Well, good afternoon, everyone. For those of you who don't know me, I'm Chris Johnson. I'm the Pro Vice Chancellor of Engineering and Physical Sciences here at Queen's. And I'm fantastically pleased to invite you to this joint lecture on behalf of the Royal Irish Academy, the Chief Executive Club, and the School of Maths and Physics at Queen's. I'd also like to extend a very warm thank you to Professor Angelo Bassi, a theoretical physicist who is joining us from the University of Trieste in northeastern Italy. A few years ago, I was asked by the Italian government to do a safety assessment or to support the safety assessment of the Alpine helicopter unit very close to Trieste. And at the end of the 2 days, I went to the director and I said, should I visit Trieste? And he said, why would anybody go there? There's nothing to see in Trieste. Only a few years later did I realize, or I was told, that he was from Udine, which is like asking somebody from Manchester if they like Liverpool, or from my perspective, if a Glaswegian liked somebody from Edinburgh. So I will leave it for Angelo to set the record straight in a few moments. I'd like to outline the format for today's event. Professor Bassi will give an address for about 35 minutes, and then after that, my friend and colleague, Professor Mauro Paternostro, who's the head of maths and physics here at Queen's, will lead the question and answer session. So if you have questions, the way that we've organized for it to be done is through the chat facility on your screen. And if you give your name and organization, then Mauro will pose the questions directly rather than transfer from camera to camera, etc., given the audio-visual situation that we're in at the moment. And then once the Q&A finishes around 2:40, Professor Jerry McKenna, the Vice President of the Royal Irish Academy, will make some closing remarks and pass on again our thanks for the presentation. Now, this is an annual event. The lecture series is named in honour of a Queen's graduate, John Stuart Bell. The series began in 2014 and as I said before, is always hosted jointly by the Royal Irish Academy and the Chief Executive Clubs at Queen's. And the aim is to raise awareness of the contribution of a remarkable scientist whose discovery on the 4th of November 1964 laid the foundations for quantum computing and for quantum theory. Before we go into that in more detail, I should say that the Royal Irish Academy was founded in 1785 and is the Academy for Sciences and Humanities for the whole of Ireland. Today, the Academy continues to play a pivotal role in Irish society, bringing together academia, government and industry on topics of mutual interest. And given the situation and the interest in quantum, this topic is really close to the Academy's heart at the moment, I think. The Chief Executive Club at Queen's helps forge connections between the university and the business community. And more details about that can be found online. So if we go back to John Bell, he's most famously known for his theorem, or Bell's theorem, that bears his name, which is called a benchmark in quantum mechanics and experimental physics. And it resolved a decades-old dispute showing that Einstein's views on quantum mechanics were incorrect. I always, when I read these words of introduction each year, I'm just waiting for somebody in the Q&A to ask me a question on the basis of this, which I'm totally unqualified to answer. So at any point, I would have to pass this across to Mauro and his colleagues. But John S. Bell was nominated for a Nobel Prize and was described as one of the top 10 physicists of the 20th century by the Institute of Physics. And it was first, the theorem itself was first published 57 years ago today, which is why we hold this lecture annually on the 4th of November. He was born in 1928 in Belfast in a working class family and attended Belfast Tech before starting as a junior lab assistant in the physics department at Queen's. The professors there recognized his ability and encouraged him to attend lectures. He enrolled the following year for a degree. He achieved 2 first-class honours degrees and went on to complete a PhD in England before working at CERN in Switzerland. And I think people recognise that his work has changed not only Queen's, Ireland, and also the world in terms of the impact of what he has achieved. So if I go on to Professor Bassi, who in fact was born in Udine, even though he works in Trieste, which must be a very difficult situation from my very limited experience. He was awarded a PhD in physics in 2001 from Trieste, Subsequently was postdoctoral fellow and visiting scientist at ICTP in Trieste and a Marie Curie fellow at the Ludwig Maximilian University in Munich. He rejoined Trieste in 2006, where he's now a professor in the Department of Physics. He's published more than 100 articles in international journals and organizes many conferences and workshops and schools on quantum mechanics and similar topics. He's chair of the Cost Actions, Fundamental Problems in Quantum Physics, and QT Space, Quantum Technologies in Space. And that's a connection with me. I'm working on the quantum key distribution satellite at the moment, but I don't deal anything to do with the quantum aspects. He's PI of the Horizon 2020 FET open project on testing the large-scale limits of quantum mechanics. And he was profiled by the New York Times Magazine in June 2020, where he was labeled the rebel physicist on the hunt for a better story than quantum mechanics. I don't think I can do any better than that as an introduction. So without any more delay, can I pass over to Professor Angelo Bassi, who will give this year's John Bell Day lecture entitled Spooky Action at a Distance. Thank you.
No. Okay. Can you hear me well? Good morning, everybody. Okay, so thank you very much, Chris, for the introduction. Actually, yes, I'm in a difficult position because I am from Udine, and even worse than that, I married a wife from Trieste. So now I have to be careful in judging among the two cities. And my talk actually will be precisely about the question you raised: why Bell is known for, in a sense, to have proven that Einstein was wrong. And that's precisely what I will talk about today: Bell inequalities, but not only the inequalities. I hope to convey the message of what the inequality mean, what they entail, and what they will imply for the future of physics. So let me start. So this is, okay, sorry, I had a difficulty. Okay, so let me first say in just a couple of words what quantum mechanics is about. Of course, this is not a lecture about quantum mechanics that will take me a long time. So I will give you just a very sketchy idea of what it is about. So first, classical physics. So classical physics is about particles moving in space along trajectories. Those of you that have taken any course on classical physics, they probably have learned about Newton's laws that tell you that the particle moves in a straight line unless there is a force that makes the particle deviate from the straight trajectory. So there are lines, there are trajectories, there are particles moving, being always in a definite position, which can change from time to time. Quantum mechanics instead has a completely different view about the behavior of physical systems, and especially of microscopic physical systems. The description that quantum mechanics provides is that of waves. So physical systems, particles, atoms, molecules, protons, whatever, they are described by waves, and these waves diffuse over in time. They propagate in different directions. They can split in two or more parts. They can recombine and interfere with each other. So the picture is more or less, which is not fully correct, but sufficient enough for today. It's like that of water waves. Water waves are everywhere in a shaky ocean, and they can break against rocks and they can recombine and all these kind of things. This is the way that quantum mechanics describes particles. And then you have the following situation, that when you have an atom, for example, I will talk often about atoms and particles or whatever. So the wave describing the atom can be in the superposition of two parts, one part on the left, one part on the right, one part here, one part there. Like again, think of two ocean waves, or an ocean wave that is split into two parts, and the two parts survive simultaneously. There is a superposition. Which is an experimental fact by now. One can see these quantum effects every time, basically in the laboratory. And actually, that's the main reason why this wavy description of nature was brought up by quantum mechanics, to give an explanation to the new coming experimental evidence from the microscopic world. But then you don't need to have only one atom. You can have two atoms, three atoms, a molecule, many molecules. And in principle, you can also have so many atoms that form a cat, like Schrodinger's cat, whose wave can be in a superposition also of being here and there, left or right, or as Schrödinger put it originally, just to dramatize the situation, not to be any cruel against the cat, to be dead or alive. Just to show that if you take quantum mechanics seriously, you have a problem. So this is in a nutshell, the main feature of quantum mechanics, especially with respect to classical mechanics, a wave description also of matter, also of elementary particles, of those particles that are considered to be unbreakable. According to classical physics, they are stiff, they are always in a definite location. According to quantum mechanics, the behavior is more subtle. But then the question emerges, and that's the key question out of which the Bell inequalities come out. What does it mean that an atom is described by a wave which is in a superposition of being here and there? Does it mean that the atom is both here and there? It is an ubiquitous atom that can be in two places at the same time? Or does it mean that the atom is either here or there? Or does it mean that the atom also is a wave and the atom really split in two parts, half atom here and half atom there? So these are important questions. These are fundamental questions because they regard our understanding of nature, the real understanding. So what nature really is about. One thing is to say how nature behaves, and these are important questions. Which kind of complex system they give rise to, which kind of technologies we can achieve with the nature, which kind of experiments we can do with that. These are all important questions. But if you go to the bottom, the very fundamental question, this would be the question that emerges from quantum mechanics. What does it mean for a quantum system to be in a superposition? What does it mean for the Schrödinger cat to be in a superposition of dead or alive, or less dramatically, walking in one direction and walking in the other direction? And actually, these were the questions that were raised by the scientific community about 100 years ago, when quantum mechanics started to pick up, when it was clear that nature was not classical, but it was in some sense quantum. And there were two opposite sides, one championed by Einstein, and the other with Schrödinger and Bell in the later years with Planck, and the other one, de Broglie, and the other one with Bohr and the famous Copenhagen School of Quantum Mechanics. Bohr was in favor of the quantum description of nature. Einstein was unsatisfied with the quantum description of nature. And in particular, he was not understanding what the meaning of a quantum superposition was. What does it mean, again, that an atom is in a the wave of an atom is in a superposition of left, right, here, and there? According to Einstein, the only possible answer was, well, that means that the atom is either here or there, because we never see, in an experiment, you never see the same atom into different locations. That never happens. The atom is always somewhere when you make the measurement. The question is, what happens before the measurement? The question, so the prediction of the future measurement. So for Einstein, a wave which is here and there at the same time means that the atom must be somewhere, either here or there. It is simply our ignorance about the state of the system that is reflected in the wave function. The wave function is here plus there because we don't know whether the atom is here or there. It's like when you toss a coin. Before tossing the coin, you do not know whether it will be heads or tails. So you have to assign probability. The probabilities will be 50 and 50. But then when you toss the coin, it will be either heads or tails. A very simple explanation of the situation. And the wave function is a new way of describing this ignorance and this probabilistic behavior of microscopic systems. But that means that the wave function does not contain the complete description of the situation, because the atom is somewhere. We simply do not know where. So the wave function doesn't give the full information, gives only the best information we can have, not the complete information. And so this position of Einstein is called incompleteness. And actually the 1935 paper by Einstein, Podolsky, Rosen, the famous EPR paper with the paradox is called, I hope I remember the title correctly, Can the quantum mechanical description of reality be considered complete? So the issue of completeness of quantum mechanics. There is more in physics than what described by quantum mechanics. Fine. On the other side, instead, there was Bohr and the Copenhagen School that were taking a completely and radically different position. They thought that there is an intrinsic limit to our knowledge. It's not possible to know with precision where the atom is located unless you really go and look. But if you don't go and don't look, then you cannot say anything about the position of the atom. So when you have a superposition, atom here plus atom there, It's not that the atom is either here or there, here and there, up here, up there. There is simply no ontological fact. There is no fact whatsoever about the position of the atom. You cannot make any physical statement about the position of the atom. The only physical statement you can make is about the probability of finding the atom somewhere. And then the wave function will tell you that if you make a measurement and you look where the atom is, the atom will be 50% of the times on one side and 50% of the times on the other side. So the wave function tells you everything there is to know from the physical point of view about the state of the system. There is nothing else beyond quantum mechanics. Completeness, the completeness position. The wave function gives the complete description of the state of the system. Again, I hope I can convey you the importance of such questions that are partly philosophical and partly physical, because now, physicists are debating about the very nature of the constituents of matters. Are they solid things that are always somewhere in space, as people thought since ever? Or now we have really to give up, we have a limit to our knowledge and to our physical knowledge about the states of the system. And that's why the debate 100 years ago and also today was a very heated debate, because it's, again, the very understanding of nature, the foundation of physics. So the Copenhagen school historically was the dominant school, but Einstein never gave up in trying to convince the colleagues about the correctness of his interpretation, of his position towards quantum mechanics. And he came up with the following argument to further convince that the quantum theory must be incomplete in describing nature. So take a box, take a particle in a box. Then, according to quantum mechanics and according to the Schrödinger equation, if you wait for some time, the wave function of that particle or atom, whatever you want, just one, to make it simpler, will diffuse and will be, after some time, evenly distributed within the box. And there the box is represented by the red box, and then the wave function by the lighter red shaded area. So that's the wave function, uniformly distributed. Now, without opening the box, you cut it into two parts, and you move one part to the left and one part to the right, arbitrarily far from each other. And then again, also the wave function splits. Half of the wave function will be within the half part of the box, and the other half of the wave function will be on the right part of the box, of the half box. So we have created a superposition for the wave function of the particle, here plus there, left plus right. Again, what I told you before. And then the question that Einstein asks is the following: where is the particle? So again, where? It's always the same question. What can we tell about the particle, about the most primitive property that an object usually has? Position. Before saying that an object is ugly, nice, big, small, tall, whatever, it should be somewhere in space. So where is the particle? Then Einstein considers the two situations. So if you take the incompleteness point of view, that the wave function does not represent the entire description of the state of the system, but that's just our ignorance, then it's again more or less like coin tossing. The particle is somewhere. Like when you toss the heads or tail, is already in the coin. It's not that it emerges only after tossing the coin. So the particle is somewhere. In this picture is on the right. It could have been on the left during the process of cutting the box into two parts. The particle is somewhere, we simply do not know, because we didn't open the box, we didn't check, so we don't know where it is yet. It's on the left, it's on the right, we don't know. And the wave function, again, represents our ignorance about the position of the particle. Very simple, very naive position. Then when you make a measurement, so we open, for example, the left box that is with us, then we look inside, we do not find the particle, then we conclude that the particle must be on the other side, on the left half of the box. Very simple interpretation. So the particle was always there, it's been there, it's simply that our knowledge about the state of the system has changed, because before I didn't know, then I looked inside and I gained knowledge about the position of the particle. My knowledge changed, nothing particularly dramatic. Knowledge changes. As soon as we learn, we know something, we have some information, our knowledge about something updates, upgrades, and becomes sharper. But then as Einstein asks, what happens now if I take the completeness assumption, so that I declare that there is no fact about the position of the particle before a measurement. One cannot say that the particle is on the left or the particle is on the right. There is simply, nature is not like that. The particle is in some sense nowhere before making the measurement. Well, one makes the measurement, opens the box on the left, one finds that the particle is not on the left, then we conclude that the particle must be on the right. And then here something important for Einstein occurs, a non-local effect. So Einstein says, if that's the situation, then my looking in the left box created reality both on the left and on the right. On the left, the reality is there is no particle. On the right, the reality is there is a particle. So in some sense, the particle materialized on the right, even if the right part of the box was very far away from me. And that's clearly non-local effect. That is, non-local means something that happens more or less instantaneously at a distance. And Einstein couldn't accept that. Einstein was a strong supporter of locality, which is also supported by experimental evidence. Every disturbance propagates at a finite speed, which can be as fast as the speed of light, but never larger than the speed of light. Here, the game could have been played with two boxes being extremely far away from each other. Distance doesn't matter here. Einstein strongly believed in locality. He was incidentally the inventor of general relativity, which is the queen of local theories. And so he said, since a complete attitude towards quantum mechanics leads to non-locality, and I think that non-locality is wrong, the world must be local, then it cannot be complete. Quantum theory cannot be the complete description of physical reality. So that was the conclusion of Einstein. The 1935 EPR paper, for those of you who know that, is just a more elaborate way of saying exactly the same things that I presented to you now with the boxes. So now we come to Bell. So this was the situation till the mid-30s. Then things died out because the scientists were more interested in improving quantum theory, in developing quantum field theory. There was also a war in between. We should not forget about that. So there was the boom after the world of quantum field theory, the successes of high energy physics and particle physics. But then something emerged back from the ashes in the 60s, precisely thanks to Bell. And I will try to convey you the message of Bell inequalities with the following game. So, okay, so the question of, so first, the summary so far, the request of locality poses a problem with quantum theory. Okay, so what did Bell do? What was the major achievement of John Bell? I hope to convey this to you with the following game, which might look silly, but the important thing is the message. So take two teammates, so Alice and Bob, and they play the following game. They close in the two boxes, like in the old times, the TV games. So they're in a far away locations. They cannot communicate with each other, and you can make sure that no way they can communicate with each other. There are no mobile phones, no connection, nothing. They are just fully isolated from each other. And there are two audiences, one by Alice and one by Bob. And the role of the audience is to give Alice and Bob a card. So there are several rounds of the game, and each round, the audience gives Alice and Bob a card, almost more or less simultaneously, if you wish. A card with a number written on the card, 1, 2, or 3. The audience chooses which number to give. The two audiences can agree or not agree. It's up to them. They have full freedom on which number to write on the two cards and hand them over, one to Alice and one to Bob. And the game is repeated over and over in time. Alice and Bob have no control on the number given on the card. What Alice and Bob do is to write on the card they receive either yes or no, or no. Again, it might sound silly, I will come to the point. So they receive the card with the number, they look at the number, they write yes or no, and they give the card back to the audience. And the audience collects the card. Round 1. Round 2, 2 new cards to Alice and Bob, 2 new answers, and so on and so forth. That is as silly. Okay, so here I just made an example. So I highlighted the first 2 rounds, and then you can see a bit blurred, but you can see the rest if you wish. So in the first round, Alice is given a card with number 1, Bob is given a card with number 3. Alice answers yes, Bob answers no. Nothing dramatic. Round number 2, by coincidence or whatever, Alice receives a card with number 2, and Bob also receives a card with the number 2. And they both answer yes. And so on and so forth. If you wish, you can read all the 8 rounds I have displayed here. So apparently, it's a really silly game. The cards are given randomly because the audience decides so, and Alice and Bob randomly answer yes and no. It seems to there's nothing special about it, except for one thing, that every time that Alice and Bob are given a card with the same number, they always give the same answer, either yes or no. They can give the same answer also if they receive cards with different numbers, but we don't care about that in the moment. The important thing is that every time they receive a card with the same number, they give the same answer. Now, nowadays, with all the TV games and all the TV movies and tricks and whatever, this doesn't sound so much astonishing. But think to be back about 100 or more years ago, when there was no telecommunication, no internet, no nothing, and there are these 2 guys far away from each other, that every time they receive a card with the same number, they magically give 100% of the times the same answer. Well, Alice and Bob claim, look, we are telepathic. Challenge us. You can choose whatever numbers you want, but be sure that every time you choose the same number, we will give the same answer, even if we are far away from each other. We are telepathic. Telepathy is another way to say non-locality. Telepathy is the ability to communicate more or less instantly at a distance with someone else in non-locality. So this issue that non-locality that comes in. And they make their fortune with them. But then after some time, someone which would represent Einstein finds the trick and says, no, look, there is nothing deep about that. I don't believe in telepathy. It cannot be that there is this non-local effect. There must be a trick behind it. And the trick is that they agreed beforehand on all possible answers. Before starting the game, Alice and Bob wrote a book with all combinations of cards they could receive and all the possible and all the answers they would have given. And here again, I give 2 examples of the book. Alice and Bob, in this book, they agreed, and they have 2 copies, 1 each of the book. They agreed that if they, in the first round, if they receive the card with number 1, they will answer yes. If they receive a card with the number 2, they will also answer yes. But if they receive a card with number 3, they will answer no. In the second round, we change, just to make things complicated. If we, in the second round, we receive a card with the number 1, we answer no. If we receive a card with number 2, we answer yes. If we receive a card with the number 3, we answer no. And so on and so forth. So this long list of all possible answers. And then you can easily explain what I showed you before. On the right, you have the same thing I showed you before. An audience, in the first round, the audience decided to give Alice the card with number 1 and to Bob the card with number 3. And then Alice answered yes and Bob answered no. But then, as in the second round, as soon as Alice and Bob are given the same card, number 2 in this case, they give the same answer, yes. So very simple explanation of these correlations. Going back to the particle in the box, it's the same thing that Einstein was discussing in more physical terms. The particle can be either on the left or on the right. If it's on the left, it's not on the right. If it's on the right, it's not on the left. So there are these correlations between left and right. I believe in locality. There cannot be telepathy. Therefore, this correlation, this property, the particle being somewhere, was all before the measurement, was there before the measurement. It was not created during the measurement. Like here, Alice and Bob, the answers of Alice and Bob were decided, existed long before the game started, not just during the game. Alice and Bob couldn't make the answer during the game, otherwise they would be telepathic. And that's the situation again in 1935. Now we come. So this is the basic point. The basic point, so not telepathy. In other words, the denial of non-locality. The world must be local. Then Alice and Bob must have agreed upon the answers beforehand. So our knowledge, so we are part of the audience, our knowledge about the game was incomplete. We didn't have the entire information. We didn't know about the book with all the answers written there since the very beginning. Locality demands incompleteness. Otherwise, there is a problem with quantum mechanics. Well, now I'm coming to the end, because now the point of John Bell was very simple. John Bell did something extremely smart that no one did before, and actually the thing that is astonishing, that in the end it is extremely simple, but that's the power of strong ideas are always, or often, let's say, simple ideas. Bell said, well, let's talk about that. Let's check the entire statistics of questions, of answers given by Alice and Bob, not only when they receive a card with the same number, but also when they receive a card with a different number. Let's see what happens. So if they have this book, if there is this book with all possible answers already agreed upon, then the situation is the following. So take all the possible combinations. So in each round, there are 9 possible combinations. Alice receives 1 and Bob 2, or Alice receives 2 and Bob 1, Alice 1, Bob 3, or Alice 3, Bob 1, and so on and so forth. 3 times 3, 9 combinations. Then out of these 9 possibilities, possible pairs of cards that Alice and Bob receive in each round, at more than half of the times, they should agree on the answer. They should both give either the answer yes or the answer no, whether they have the card with the same number or card with different numbers. So here is just in round 1. In round 1, they agree that they give yes, answer yes to card 1, answer yes with the card with number 2, and answer yes, no, sorry, for the card with the number 3. Therefore, if the following situation happens, that Alice receives 1 and Bob 2, or Alice 2, Bob 1, or Alice 1 and Bob 1, or Alice 2 and Bob 2, or Alice 3 and Bob 3, so 5 situations, they will give the same answer. Either both yes or either both no. In all the other cases, they will disagree on the answers. One of the two will say yes, and the other two will say no. So what is, and you can run, if you wish, you can run this same for all the possible situations, and you will see that in every round, the number of agreements should be larger than the number of disagreements. And that's Bell's inequality. This is the essence of Bell inequalities. If there is locality, because this is the starting point of all the discussion, if there is locality, then Alice and Bob should play the game in a specific way by giving a larger number of agreements, same answer, with respect to the number of disagreement, different answers. Bell inequality. Well, let's look at the game. Now I give you the first 8 rounds, all of them. You can count the number of times they agree and the number of times they disagree. And so in the first round, one answered yes and one answered no. They disagreed. In the second round, they agreed. The answer is in both cases yes. In the third round, they also agreed. Answer no, and so on and so forth. The number of agreement is, statistically speaking, the same as the number of disagreements. So the game is not as predicted by Bell inequalities. And this is the essence of Bell inequality. So locality, that was the starting point. Locality implies the inequality, Bell's inequalities. This is the major result of Bell, which put together the first intuition by Einstein and then further developed that. Well, experiment says that the inequalities are violated, and they have been repeatedly over and over violated in experiments with quantum systems. And so we have non-locality. The world is non-local. And that's in this sense that Bell proved that Einstein was wrong, because Einstein thought the world must be local, and so the quantum theory, there is something wrong with quantum theory. Bell comes to the point, look, I don't care about quantum theory. It might be correct, it might be wrong, but if the world is local, then you have my inequalities. Nature violates my inequalities, so the world is non-local. I'm sorry for you, Einstein. So, and that's the conclusion. So nature is non-local, and it poses a problem to physics, because it conflicts with relativity, it conflicts with special and general relativity, which is the other pillar of modern physics. The conflict is not direct, and that makes things even more subtle. And that, unfortunately, I cannot have the chance to speak about this. This non-locality cannot be used to superluminal communication. It would be fantastic, like in a science fiction movie. This is not the case, and that adds extra mystery to the situations. The thing is that simply we do not know. We have reached a limit to our knowledge, and there is more that we need to know, and we do not know yet. Let me just 2 slides to conclude. So I look beyond. Let's see if it. Yes, I look beyond. So this non-locality has a special character. This non-locality is insensitive of distances. While usual interactions depend on distance, this non-locality is independent of distance. The two, Alice and Bobo, the two particles in the box, can be arbitrarily far away from each other. Doesn't matter. Space doesn't play a role. And this is my personal point of view. That's why I'm saying look beyond. This is my look beyond, if you wish. Before that, that's the claim of Bell's theorem. Now, my perspective, my take into that comes in. My point of view is that telling us is that we need a new theory of nature, a new theory of nature which is not based on space and time, because space and time do not play a role for this correlation. Space and time are not fundamental. This is not the status of current physical theories. It needs something more, new theories of nature. I want also to give a look beyond physics, I would like, just to conclude in a happy way. So if you take again all this seriously, and if you consider the history of the universe from a quantum perspective, then all particles must be correlated to each other. There is this non-local correlation that are scattered all over the universe. So the idea of an isolated system, fully, as much as possible, isolated from the rest of the world, doesn't exist. We are fully connected to each other. And I think that is a happy ending of Bell's great, not fully appreciated contribution to our understanding of nature. And thank you for the attention.
Hello, everyone. Hello, Angelo. Thank you so much. Hello, everybody. My name is Mauro Paternostro. I'm the head of School of Mathematics and Physics and one of the co-organizers of this event. Please join me in thanking Angelo for his fantastic lecture in honor of John Bell. I think it's just fantastic to celebrate one of the greatest son of Northern Ireland and Belfast in particular, with such a insightful and very clear lecture. So thank you, Angelo. Thank you, Angelo, for your contribution. I am in charge of the question and answer session that takes place traditionally after the Bell lecture. So Angelo, thank you again for your kind availability to give us 30 more minutes of your time to take the questions from the audience.
It was an honor for me.
Sure. Thank you so much. Very appreciated, Angelo. There is already quite a robust number of questions that have been put forward while you were talking and even beforehand. So before I give room to the questions and Angelo's reply, let me just reiterate that whoever would like to put forward a question to Angelo can do it. For using the Vimeo chat facility, where you can type your question and I will read them loud to Angelo for his assessment. Okay, shall we start, Angelo? Yeah, you're okay?
I'm ready.
Okay, so picking up from the list of questions that we have received so far. Okay, Mandy, she asks, what is the biggest doubt that you have regarding our current scientific understanding of quantum mechanics?
The biggest, sorry?
Your doubt, your
okay. So I personally do not think that the quantum mechanics is the correct description of nature. So it's, of course, in a sense, it is correct because we are using that and we have learned a lot about the behavior of matter, the internal structure of matter. We can understand it, prove it experimentally, and manipulate it technologically in an astonishingly accurate way thanks to quantum physics. So of course there is a lot of truth in quantum physics. So my point of view is not from the foundational point of view, not from the broader physical point of view. From the foundational point of view, I think that quantum physics is hiding something about the real nature of of reality and of physical reality. And there was something that was asked also in the previous chat, no, Mauro. And I think that my take at the moment, let's say, is that quantum physics is more or less like thermodynamics. When people were in the 19th century, they were developing thermodynamics, and thermodynamics was fundamental for the understanding of physics and for technological development. Think about the steam engine and all the industrial revolution that actually started in the United Kingdom. So it's even more appropriate to speak about that here. And what did I say? So thermodynamics is an impressive theory, very accurate, astonishing, but it's not fundamental. Speaking about heat, temperature, pressure is relevant. Engineers still do that in a very successful way today. But these are not fundamental concepts of nature. Fundamental concepts of classical physics are particles, position, velocities. And I think that the same is true for quantum mechanics. It works, it describes a lot, it tells a lot, but it is not fundamental. There is something more behind it. What is that? I don't know yet.
Thank you, Angelo. Thank you so much. We can continue with some thought-provoking questions that have been put forward. So there is one set by Owen, and this is relatively long to read. So let me know if you want me to repeat it, Angelo. Okay. So Owen is asking if are general relativity and quantum mechanics completely unifiable due to space and time being quantized under quantum mechanics and continuous under general relativity?
Yeah, I need to read it one more time, sorry.
Yes. Are general relativity and quantum mechanics unifiable in light of the fact that space and time are quantized and continuous due to general relativity?
I would say that that's not the reason. So whether the quantization of space-time, where the fact that this continues in special relativity, in general relativity also, it's not the reason of whether you will be able to unify them or not. Take the example of electrodynamics. So in classical electrodynamics, the electromagnetic field is continuous. Nevertheless, it was quantized in a successful way. So this quantization, so if I understand correctly the question, I hope I understand correctly the question. So this issue of quantization versus a continuous quantity is not a problem for a unification. Electromagnetism was unified with quantum theory. So what happens to gravity? Well, that depends on who the question is asked to. So the general, I would like first to give the general feeling of the community, and then I would like to give you my personal opinion about that. So the general feeling of the community is that it should be possible to quantize gravity, to unify general relativity and quantum theory in one single framework. It proved to be less straightforward than people thought. Most likely now the community accepts that some reconsideration about quantum theory could occur, or even more, a reconsideration of what general relativity is telling us should be taken into account in order to arrive at a fundamental unified theory. But nevertheless, the goal is achievable. My point of view about that is that it's the wrongly posed problem. I think that there is a fundamental conflict between general relativity and quantum mechanics. Quantum mechanics cannot be a theory of space-time because in a standard formulation, it assumes a classical space-time. Measurements and observers must be somewhere in order to make a measurement and to do an observation. So and then this was clear by the founding fathers. So quantizing space and time is something that from a fundamental point of view, I cannot really understand what it means, except apart from the mathematical question of turning a classical quantity into a quantum quantity. So I do not understand what the question of quantizing gravity means, other than finding a unified theory. So one thing is to find unified theory, which I also intimately believe in. But the form of that theory is the quantum theory of gravity that people usually talk about. I'm very dubious.
Thanks, Angelo. Thank you. Okay, moving towards more the top, really, the core topic of the lecture that you just gave. So Patrick asks, if action at a distance implies the transfer of information, is this subject to a time delay due to the speed of light?
So if can you say it again? Sorry, Mauro.
Yes. Sorry for my reading.
No. I have to think.
if action at distance implies transfer of information, is such a transfer subject to a delay, a time delay, due to the speed of light?
Okay, so the thing that actually skipped in my talk, because that would take too long time to really explain in detail the reason why, is that this action at a distance, this, let's call it non-locality, just to be on the safer side, this non-locality, which I do think it's action at a distance, but not everybody in the community would agree on that. So that's why I use the word non-locality. This non-locality does not imply superluminal signaling. And if one goes into, or any transfer of information at speed faster than the speed of light, and if one goes into the reasons why, this is the superluminal, this action at a distance, let's call it, does not imply superluminal signaling, is that when we play with quantum system, so we do not have control of the outcome of the measurement. It's like tossing a coin. You cannot know whether it's heads or tails, more or less. So you the quantum system. And this uncertainty in the behavior of quantum systems blurs the possibility of, cancels, let's say, the possibility of doing superluminal communication. So, of course, according to standard quantum mechanics, there is no locality, but this no locality cannot be used for a faster than light transfer of information. Transfer of information is always subluminal. And in that sense, it's compatible with what we know about physics and relativity. But I want to add one important point. That again, if one goes into the details of that, one sees that by magic, at the moment, purely by magic, the kind of uncertainty in the behavior of quantum system is precisely the right one to cancel this action at a distance. And then the question comes, why? Why that? If you modify quantum rules a little bit, you would be able to do instantaneous, I mean, really in a strict sense, instantaneous superluminal communication with faraway parties as soon as you tune differently the quantum rules. So why are the quantum rules like that? So, and then the answer depends on the person you ask to.
And to how much beer we have drunk, Angelo. I'm jumping between questions. So there is one that is again very much at the core of the duality between Bell and Einstein. So unfortunately, it's an anonymous question. So sorry, Angelo, for that, but the question is good. So usually, the locality issue is associated with the realism problem. What does it mean?
Okay, so this is something that I strongly object. So I tell you what it means, and I tell you why I'm strongly against it. Actually, it's not that I am strongly against it. Bell was strongly against it, to be on the safe side, and I with Bell. So it's not my merit. I don't take the credit for that. So the argument I presented to you in the talk was made of two parts. The first part was Einstein. Locality means incompleteness. Incompleteness in the sense I specified before, that properties are already there before measurements. That is what is being named, for reasons that I don't understand, or I partly understand, let's say, they've been named realism in the community later on. So you can phrase the first part, when I spoke about incompleteness, you can phrase it as locality means realism. Then Bell's inequalities, the one on 1964 that are celebrated today, developed the second part, that incompleteness, so what are called hidden variables, what is called realism, imply the inequalities. Now, what is the logical mistake that people make? The logical mistake that people make is that instead of saying locality means realism, that means inequality, they make the mistake to say reality and realism imply the inequalities. Therefore, if the inequalities are violated, you can choose which of the two to give up, realism or locality. But this is not Bell's theorem, and Bell was very clear in later papers where he came on the same subject, and he made it clear that the assumption is only locality. So locality implies the inequalities, the violation of inequalities imply the violation of locality. Realism doesn't play a role. the fact that it plays the role in the discussion is the reason I told you before, that there's been a misunderstanding also by distinguished scientists in assuming that Bell implied two assumptions, locality and realism. That is not correct.
Thank you, Angelo. Thank you so much. Now, jumping a little bit topic, okay? So, and now we are digging into your rebellious nature and why you are the rebel in quantum science. So, Hannah asks, how close do you think we are to confirming whether or not collapse models are valid?
Ah, good question. Because I mean, then it becomes personal, and in the sense that the answer from my heart would be soon, but really I know it's I really do not know, because it depends on whether, so assume, let's assume for the sake of the answer that collapse models are correct. So the nature really goes like collapse models. Which maybe, is not...
Angelo, maybe for the sake of the non-experts,
sorry.
Maybe you can give
yes. Yes, sorry, yes, you're right, Mauro. So what is standard quantum mechanics? Standard quantum mechanics tells you the wave function, the function I explained before, evolves with the Schrödinger equation. So it diffuses like water waves, like any wave, except when you make a measurement, it collapses. And the issue is that why one behavior versus the other behavior? Well, collapse models simply put the two things together. They merge the two behaviors, the Schrödinger, the usual diffusion of a wave with the collapse during the measurement, in one single equation, which takes a bit of both. And you have a mixed dynamics where the wave function spreads, but not as much, and does this kind of thing. So these are collapse models. And as such, since there is a new equation, there are new physical predictions, which can be tested experimentally and verified or falsified. So suppose that nature really goes like collapse models, that the evolution is not a clean evolution of Schrödinger, but this shaky evolution predicted by collapse models. The question is where at which level you can see a signal of collapse models. And the problem that we have from the theoretical point of view is that we do not have a clear indication of where the signal should lie. So should you do this kind of experiment or another kind of experiment? So it's an issue, if you wish, with the more famous problem of dark matter. So dark matter seems to be there around, but no one can see it, because since it's dark, we don't know what it is really about. So it's difficult to make precise prediction about the dark matter. The same with the collapse model. So I hope in my lifetime to see something, of course, but other than this, there is no strong theoretical reason to say it should be with this experiment that can be done in 5-10 years, or this other that needs 100 years.
Thanks again, Angelo. Okay, digging into probably more personal views. Okay, so Chris, he asked, what is the greatest unknown, in your opinion, with quantum physics that you would like to understand?
It's precisely quantum non-locality. My answer is precisely that. I think that if it were not for non-locality, which is due to entanglement, which is rooted in quantum theory, so if you take away these features of quantum theory, then quantum theory is a very simple theory, amazing, that's no question about that, but from the point of view of understanding, would be nothing worse than electromagnetism or general relativity. Is just a new theory of nature. It is the entanglement, this mathematical state, which shows up physically with this non-local correlation at a distance, that make things mysterious. And I think this is the biggest obstacle now that we have in understanding, or I want to take it in the positive sense. It is the biggest hint that we have that there is something that we should understand and we do not understand at the moment. But we are still so much filled with the all-the-time physics. Let's be ironic and call general relativity all-the-time physics, even if it's not, with our idea of a local world that comes from a long history of science, very respectful history of science. So we are so much used to a certain way of thinking that that's my personal point of view, that I think that we are not able, and we do not have yet the courage to make and the correct intuition also, to build a different theory of nature like Einstein did with the general relativity with respect to Newtonian gravity. The right guy has to come, and he or she will come one day. Don't know when.
Angelo, the answer is perfectly in line with the next question that I wanted to raise to your attention. So Owen asks, as the field of quantum mechanics pushes mathematics to its limits, do you believe the pattern would continue and the next breakthrough in the field will come from new mathematical insight?
Not clear actually, because so suppose that tomorrow they make the experiment that they find this extra noise, for example, predicted by collapse models, or something that is not predicted by quantum mechanics. Then the experiments won the race, and then of course the community will jump on understanding what's going on. So the answer is not clear at the moment. We have to. They go parallel. We have to let the experimentalists do their job and be as fast as possible and as precise as possible. And at the same time, theoretical physicists. It could be that now there is the genius somewhere that is working on the new theory. It's really unpredictable to me. I wouldn't know what to answer. I just say that there is work to do. Let's say it's not like Laplace. When was Laplace? I think in the 18th century, that if we know the position of all particles in the universe, we can predict the entire past and future. So this certainty that we have understood nature. I think that we live in a privileged times, at least for me, privileged times, because we know we don't understand nature. Of course, in a fundamental sense, I don't want to be misunderstood. We understand a lot, so I don't want to be catastrophic. But in a fundamental, deep sense, we do not understand.
Angelo, there is a question by Fumin, going back a little bit to the interplay between relativity and entanglement, or the correlations entailed by entanglement. So Fumin asks, states of entangled particle change simultaneously in one reference frame. Will it be different in another reference frame? So will such event be different in another reference frame?
Well, that's not an easy question, because let's say what happens according to standard quantum mechanics. With standard quantum mechanics, if you have two systems, so an entangled pair of two particles, you measure here, you instantly change the wave function everywhere, and therefore. And it's like the particle in the box before. And this is against relativity. If you take it this way, it is against special relativity, because now if you take a different inertial frames, what it is instantaneous is not instantaneous anymore. And there is a conflict between the collapse of the wave function as we know it, which is certainly superluminal. That's again another way to put Bell's inequalities. The violation of Bell inequalities imply that the collapse of the function, if existing, is superluminal. And relativity. So since there is a conflict, you cannot say what happens, because you can say from the theoretical point of view, you can say what happens only when you have a coherent idea, coherent picture, coherent theory. Here you have an incoherent situation. Now people try to make it coherent. And then there are different ways of making that, and I think that none of them is truly satisfactory one, because either you keep the collapse of the wave function, and then you have to deal with the fact that it is non-local, end of the story, because if you have a local collapse, you do not violate Bell's inequalities, and Bell's inequalities are violated. Or you remove the collapse of the wave function from the theory, but then you don't know what's going on, because without collapse, you don't have definite outcomes emerging out of measurements. And there is a problem. It's simply a problem that has been underestimated, under-considered, you say that in English, not really fully studied. It is a problem that is still there, and there is, at least to my knowledge, there is no clear answer.
Thanks, Angelo. Okay, let's move towards a more feet on the ground, let me say so, approach to your work. Okay, so wondering about your work. So there is Neve asking, what is it like being on the committee for quantum technologies in space? Well, actually, Angelo was one of the main motors for the translation of technology, quantum technologies to space applications. So, how is it?
Together with you, we did it together.
Go on, man.
No, that's true. So what is it like to be in the committee?
I guess the question is, which are the challenges in driving, so to say, the efforts towards the translation of quantum?
Well, I think, okay, so the biggest challenge from a European point of view is coordination of activities. So this is the strong and at the same time the weak point of research in Europe, to be fragmented in the end of the day because of the history. So there are independent countries that try to talk together, but they're still independent with different cultures, different ways of approaching things, different capabilities, different also power, economic power, whatever. So that's a richness in the sense, because there is a variety of approaches, a variety of solutions which can be used and studied and compared to see which one is the best. But on the other hand, on the downside, there is this fragmentation, this lack of coordination. I think, no, you would agree, tell me now if you would agree on this, that to coordinate different countries and to try to create a common language, a common background of challenges that should be taken into account and should be considered, some priorities to be given, and possible ways to move forward. I think that was the most fascinating, at least for me, it was the most fascinating part. So you can compare with China, which is now the easy competitor because it's the strongest competitor, especially in the field of quantum technologies. China, in a sense, as far as we know, at least, is on the opposite side. So they have a one-man show. It's a one-man show, a remarkable scientist that is running the quantum show, the quantum, I don't want to call it a show because that's not generous towards him. So the quantum program in China, and it's very successful because there is no issue about coordination. There is one man running the program. But the variety of possibilities that we have in Europe are not there. So if they fail in a big way. They're not failing, actually. They are. And so I think that is and I think that this is the difference, again, the richness and the beauty and the difficulties of being in these committees, to try to create a common language out of what we think it's a common country, Europe, let's say, a common culture in a broader sense, let's say, and to work together towards reaching major goals.
In my opinion, if I can just chip in my opinion, this is not very different from the race to conquer the moon. It's more or less the same. So it's the reckoning that you need a major scale effort to conquer completely unexplored territory. Okay, but this is not about me. So going back to the questions, Angelo, if you still have the patience to pick a couple more. Okay, so this is really going towards your personal history in a sense. Maria asked, when did you know you wanted to study physics, and why did you want to do that?
So that's a question that always embarrasses me, because I should try to give a smart answer, but the real answer is that I don't remember. But what I really, because when I was in high school, physics was not, I don't know, I don't remember it was on top of my list. But what I know that was on top of my list is the desire to study. I said it again 1 hour ago, I really like to study and to learn. So in that sense, I knew I didn't want to be an engineer, in a sense, not that the engineers don't study, but let's say. And so not a lawyer, not whatever. So for reasons that I really cannot remember, but it was certainly, I felt inside that I wanted to do physics, and I never regretted it. I think that it was something just inside me, that to understand the world around us, but I knew that I wouldn't be able to do that as a philosopher. That's not the way I would be able to think and to understand things. It was as a physicist, and so with the lack of real understanding of what it meant to be a physicist, I took a physics degree and I never regretted it.
Can I maybe unduly, so I'm chipping in with my own question, okay? So I apologize to the audience for stepping in. But have you ever lost, or do you think you have ever lost, even for a tiny bit during your career, the childish approach to asking questions and wondering about things that are the end of the day are what makes our daily working day?
Well, if we lost, you mean distracted by other things? Yes. If in that sense, yes, many times, because I mean, again, the academic life is a complicated life. It's not the thing that the scientist that sits under the tree waiting for the apple to fall down. That's not like the academic life. There are many things, and then you want to be part of the community, being part of the community, exactly you want. It becomes natural to be part of the community, and then you work for the community, and that brings responsibilities, coordination activities, as we were saying before, and many other duties. But so distracted, but never lost, not for a moment. I wouldn't say that. It was always in my mind. I have less time to think about it.
Thanks, Angelo. I think I want to conclude this question and answer session with, again, a tough question. It might be opening up, say, a completely new environment, right? So, but the question is good, and it will be thought-provoking. Again, unfortunately, is an anonymous question. Do you believe that the wave function is an ontic state?
Well, I mean, ontic in the sense that it represents reality, yes. I think that's in a way pretty clear. Then, so I have little doubt about that. The question is, in which sense it is an ontic reality? Because it could be a primitive reality, like positions for classical physics, or a derived reality, like temperature. Temperature is real. If the body is hot, you get burned. So it's something very real, temperature, but it's not fundamental. So the question about being ontic, I have no issue about that. It is ontic. What that entails, so if you have wave function floating there around, no, like there is no temperature floating there around. Temperature is just a collective property. That is a different story. And I'm not sure, but I'm inclined to think, let's say, that the wave function is a ontic, but not primitive, a derived collective property. Expressing, I can say more about that. Sorry, that's if I have just 30 seconds. Then I come back again just to give the due tribute to Bell and nonlocality, that if it were not for Bell, for nonlocality, let's say, and for entanglement, the role of the wave function is highly trivial. So take one isolated particle, nothing else, not entangled. The wave function has a very highly trivial role. It can be just a way, it's just a classical uncertainty about the position of the particle. It is entanglement, and it is nonlocality that give a special role to the wave function. So the wave function is simply, for me at least, the way we encode and we are capable of describing a crazy world where everything is non-locally connected to each other. That's, for me, the role of the wave function.
Angelo, many thanks for this incredibly insightful and comprehensive set of answers. I'm sure that the audience, people in the audience, appreciate not only your kindness, but also, say, the openness to certain controversial questions as far as science is concerned. So you have my gratefulness and my gratitude, and that of not only that of the school, but I'm sure I can talk on behalf of Professor Chris Johnson, that of the whole faculty for taking the time to deliver this fantastic lecture.
I'm grateful to you all.
It's our honor. I am now in a position to leave the stage to Professor Jerry McKenna in representation of the Royal Irish Academy. But before doing that, I think it will be incredibly ingenuous of me if I don't thank, first of all, Joan Mallon for all the work that she has done in setting up this event and making sure that everything ran smoothly, and also to Gordon for the technical assistance. And many thanks to Porrick Dempsey, Karen Maldoni, and Brenda Carabine and Dolores Vischer This is the team, is a mixture of Queen's people and Royal Irish Academy people. That is the team that every year make sure that everything is set up on time to make the John Bell Day the important event that is not only for this university, and I think it should be for this country, but also for a budding generation of scientists that should appreciate the contribution of John Bell. Without further ado, I thank Angelo again for his fantastic lecture, and I leave the stage to Professor McKenna.
Good afternoon to you all. I'm Jerry McKenna, Senior Vice President of the Royal Irish Academy. The Academy is very pleased to be involved again this year with the Chief Executives Club at Queen's University Belfast and the School of Mathematics and Physics as we celebrate John Bell Day together. The Academy supports John Bell Day as we see Bell as an inspirational role model for the young people of Northern Ireland, inspiring them to see education and science as an exciting route by which they can fulfill their greatest ambitions, as Bell did. This year's John Bell lecture was, as I'm sure you will all agree, most enlightening and entertaining. We would like to thank Professor Angelo Bassi of the University of Trieste for his insights into the transfer of information. Thank you, Angelo. We'd also like to thank Professor Mauro Paternostro, head of the School of Mathematics and Physics here at Queen's, for moderating the questions and answers, and Professor Chris Johnson for his introduction. We also thank Professor Paternostro for his sustained commitment to the lecture series. Lastly, thank you all for attending and for your questions. Goodbye.